This video has been supported by PCBWay. Hey guys, here's a bit more grunting about the Datron Wavetek 4950 multifunction transfer standard that we serviced last time. Immediately after open heart surgery and lots of preventive maintenance, it was completely unresponsive. The reason for that was absence of an entire positive voltage supply rail on the analog board. And the reason for that was a bit tricky to find. A damaged plated through-hole underneath an electrolytic capacitor. Yeah, what can I say? I'm guilty. Go call the ppm police. I swapped that part preemptively and apparently destroyed the whole plating in the process. Oops. Oh well, easy fix. With that we are back in business, baby. But it actually took me a few more weeks to weed out all of the subtle little problems that I had missed on my first patrol. The self-check program, aka confidence test, was a useful aid there. It's actually even more helpful than a sardonic display warning if it does encounter something out of the ordinary. This is well known for other Datrons from this era, but for this model as of yet undocumented. If it throws a fault at you, say 2500 AC system AC gain, you can use the secret cheat code status config3 to put the instrument in the same states in which the tests are performed. Such an investment of precious development time into methods that facilitate repair and troubleshooting would not fly today, that's for sure. It even lets you press the sample key to get ADC readings out of every one of these pathways. That's how I found out about another subtle issue. See how that square wave has a slowly decaying DC offset immediately after entering the pathway, leading to an over 50% ADC reading at first and a 35% reading as soon as it settled down. That was caused by what I have now identified as the AC millivolt pre-preamp. A small two-stage amplifier underneath a metal can where I only replaced a blown fuse last time. 4950 offers an AC 1 millivolt 5.5 digit range. That's 10 nanovolt resolution in the least significant digit. No clue what that's good for, to be honest. But the immense sensitivity, the AC-ness, and the user's ability to accidentally connect whatever to this front end create some unique challenges. How would you protect an amplifier input from accidental high voltage connections with minimal impact on AC nanovolts? The Datron engineers thought that a melty fuse and a bipolar 2x VBC clamping circuit made from discrete NPN transistors would do the job. I found, after swapping the blown fuse, that the op-amp was also damaged. Maybe the fuse was too slow or the overload too severe, or the op-amp was assassinated by Big Sammy to encourage the purchase of a pricey replacement. Either way, in one self-test step that led to an abnormal railed preamp output into this 10 microfarad output capacitance. And in the closely following next self-test step we always caught the leftover dielectric absorption from that previous error state, finally causing a visible self-test error. Well, the solution is obvious but not effortless. I need a new first OPA 637. Oof, that is a special op-amp with a special pricing. A wide bandwidth with an ultra-low JFET input bias current. I tried cheaping out at first with a replacement part from some unreliable eBay source. Ended up receiving some relabeled fake, of course, with several orders of magnitude higher input bias current. That, together with the RC filter and whatever other resistances there happen to be in the signal path, causes a DC offset and an error in the RMS signal that is supposed to be measured here. So ultimately I had to go back to the distributor, like, yes honey, and pay $33 for the real part. Next I made a small mistake in the current assembly. I said and firmly believed that this
node is not particularly sensitive to leakage currents.
Well, Mr. Big Brain, if that is so, why don't you try and explain the use of $10 ultra-low leakage current diodes directly over the chart circuit board area? Obviously, the leakage of those parts is added in full force to the current that is supposed to be measured here. No big deal in a 100 milli or 1 ampere range, but a parallel connection of a couple of mega ohm that I would expect from a chart circuit board would almost certainly be visible in the more sensitive ranges. So I suppose circuit board material that doesn't exist anymore will have much lower leakage current. This isn't super pretty, but mechanically stable and electronically the only way, really. Next, I think I've mentioned my desire to do something about this front input connector. I really shouldn't. For things like 2-wire resistance measurements, And the sensitive ACI and ACV ranges, it does make perfect sense to have a dedicated, never-changing test lead that the meter gets calibrated with and adjusted for, exactly as intended by Datron. With universal 4mm test leads, users would be invited to use whatever loosey-goosey banana cables they have at hand, inevitably causing errors in two-wire resistance mode, possibly different thermal EMFs impacting low voltage measurements, and different reactances opposing AC measurements. So naturally I'm going to hold onto this original connector as a fallback, and the sheet metal part that holds it, but for my purposes this multifunction transfer standard would just be so much more useful if I could actually connect something to it. So I sat down and replicated this sheet metal holder with the given mounting points. The plastic front bezel is already prepared for normal multimeter style 4mm binding posts. I guess they were using exactly the same part for their multimeters, and simply drilled out a bigger hole for this much lower volume product. Good for my plans, because that makes this whole modification deliciously easy. The biggest contributor of easiness, however, is this video's sponsor, PCBWay, who is once again proving to be a valuable partner even when no PCBs are involved. Their fast and affordable sheet metal fabrication service is perfect for a part like this, where CNC machining would take way too long and be super wasteful. To have my holding bracket manufactured professionally through laser cutting and CNC bending, I only had to upload a 3D step file directly from the CAD software. No standardized technical drawings, flat patterns or tolerancing necessary if their published default tolerances work for you. Then I simply select a material and a surface finish and request a quote, which came back at $30.37 in less than an hour. Western companies would charge 5 to 10 times as much for a one-piece prototype order such as this, if you are lucky enough to find one that talks to small fries at all. So I was very happy to accept that price, and I received this securely packaged finished part 10 days later. A beautiful result at no effort whatsoever, and with much closer tolerances than were specified. Thanks PCBWay, this is going to be a fantastic modification. There's only one small detail I overlooked while planning this. The meter normally has a 1420 volt peak input rating. Not that I plan to take advantage of that on a regular basis, but I also don't want to cripple it unnecessarily. I feel like I would have to with this new connector to chassis spacing, unless I can find a way to artificially add some dielectric strength to this air gap. How about some PTFE heat shrink tubing? Sounds fancy, is expensive and exhibits opalescence, so it must be good, right? It'll even fit underneath the binding post's default plastic spacers without modification. Yeah, this is obviously meant to be. I assume the main benefits of this heat shrink tubing is a higher temperature rating and chemical immunity. I kinda bought this piece a while ago for use in an electrometer cable. The only weaknesses of pure copper hardware are oxidation and, well, weakness. After having stripped a few, I started talking these down very gently to no more than 0.4 Newton meter. The original connectors in this meter are mostly Molex KK254 series. Housings and crimp contacts for those are still available. And I'm using PTFE cables again to maintain the high input voltage rating. Maybe I should have done a quick test fit earlier. Nope, all good. Whew. Now just a new label cover thingy to hide that larger hole from the circular connector. I'm cutting and engraving this from a blank aluminium business card. I could have tried color engraving on stainless too, to match the yellow-beige Datron plastic. But wait, this isn't the right direction anyway. Any kind of metal cover here will obviously breach my hard-earned high-voltage clearances again. So while this cover came out too pretty to not show, I'm afraid I'm going to have to turn it into something plasticky instead. One last little problem that I'm aware of, and then we are finally ready to go. On the AC attenuator and preamp board there is a relay that is used to set the preamp gain by choosing one of those two hermetic foil resistors on the right. I had some strange variable DC offsets at the preamp output, a slightly different magnitude after every range change. I concluded that this part could not be trusted to lay the re anymore. Sure enough, the original nice part has a very high contact resistance that could be premature wear due to a lack of wetting current. The same reason I suspect those yellow relays in the Fluke calibrator seem to have a tendency to fail often. For an electromechanical contact to be self-cleaning, it needs to have a few milliampere flowing through it. Otherwise a cycle life specification can degrade big time. Irreplaceable relays that have succumbed to this can sometimes be massaged back to life. High frequency CPR and defibrillation at a milliampere or so. But a new one will be more trustworthy, and these TQ2Ls are still available and cheap, so that's what I chose in this case. And that is it, as far as I know. Quite a few time-consuming little problems in Datron 4950. Let's try and find out if that was worth it for essentially a 7.5-digit multimeter. My main instrument cluster is kinda approaching the desk's weight capacity, and it would produce too much localized heat if I added any more stuff to that corner of the room. So to accommodate my growing boat anchor collection, I had to start a separate branch in a different corner. Gear acquisition syndrome is no joke, guys. Go see a professional, or let the wife manage your eBay account if you experience symptoms. Of course, this outpost needs GPIB for automation. Nowadays there are low-cost microcontroller-based GPIB UART interfaces called AR488. But I want to maintain compatibility to my existing software and to as many GPIB adapter flavors as possible. So I'll be running Linux GPIB and its newly improved bit-banging driver on the Raspberry Pi, which will then take control of bus transceiver ICs on a shield. For accurate low-voltage inter-instrument connections, I used to rely on this shielded PTFE isolated 4-conductor cable. Pretty good for 95% of the things I do, but if all goes according to plan, this multifunction transfer standard against multifunction calibrator test drive will extend all the way into the spicy ranges, such as a kilovolt at 300 Hz for example, or a 100 volt 200 kHz, which is also in the capability cross-section of both of these devices. For these scary high voltage tests that take place over the course of 22 hours, I won't be there supervising every minute of it. So I felt like I needed a better, more universal set of test leads, with much more isolation, lower reactance, and still somewhat low thermal EMFs. I made these in the likeness of a Fluke product from 2 coaxial cables, and I'm pretty sure that they'll be good for everything, except for maybe single-digit nanovolt and femtoampere containment. I made 2 with 2 conductors each, not only for 4-wire resistance measurements, but also for 4-wire remote sense AC voltage setups. The 4950 attenuator apparently exhibits low enough of an impedance to cause some current flow through and voltage drop over the test leads. That's why 4-wire ACV is actually the default config for that device. Go figure. Miraculously, I found a huge, all-encompassing Python script to compare these 2 devices, ready to go in the xdevs.com archives. It will tell the calibrator what to output and the meter what to expect. Then it'll write the measurement results into an Excel spreadsheet. The cells are prepared with formulae that highlight those measurement results that are in spec green, and those that are not red. That's an immense amount of work that has been invested into this software. Huge thanks for publishing. And yeah, this'll take almost a whole day to traverse hundreds of points across all ranges. This was the result after my first run. No surprise that there's lots of red in there. I don't know how the transfer standard was last adjusted, and I've done a lot of work on all the assemblies. The proof is in the pudding, or how well 4950 will maintain its values after an adjustment towards the calibrator's outputs. Let's pretend, for the sake of a nice and round and pleasant video, that this went all smoothly. In reality, this is where I found out about the relay thing, corrupting all of the lower ACV ranges. So I had to go back, open the instrument again, disturb everything, find that part, solder, let everything recover and warm up, and start the one-day Python script again. Oof, no, everything went according to plan. See, all green now, wonderful. It remains so for multiple runs across multiple days too, so I'm reasonably confident that I caught all the gross errors this time. Only the ACV linearity still seems to have a bit of a problem. Or it's the calibrator, which I also serviced myself and never really tested as extremely thoroughly as this. Linearity is not strictly necessary for our patient today. It's primarily meant to verify voltage at frequency points of interests with spot calibrations. But thanks to a wonderful viewer, I just so happen to have the very special equipment handy that's necessary to settle the ACV argument and decide who to believe. This huge box contains a set of thermal voltage converters, the very same that all the electronic RMS converter methods we've looked at recently aspire to be. The whole set is called Holt Model 11. This is serial number 214, and it was made in 1974 in Ontario, Canada. It basically consists of 5 resistors and 3 actual current input thermocouple output converters. The one and only purpose of a venerable system such as this is to make RMS comparisons, i.e. put in one signal, measure how much temperature it generates, and then replicate that temperature with another signal such as DC voltage, which would then be its RMS representation. Let's try and use this to figure out who's responsible for the kink in Datron's ACV linearity. Each resistor comes with suggestions as to what converter to use for what voltages. Through combinations, a wide range of sensitivities between 3 and 1200 volt are covered. The halves are mated with a coaxial pattern of pins and sockets. The result looks like a thermos or a CNC spindle with some imagination. The input connector is a General Electric Type 874. A gender fluid RF connector that was popular between the 50s and 70s. After which it was mostly replaced by Type N and B and C connectors due to manufacturing costs. I bought a new old adapter just for this purpose. I'll use Keysight 3458A, the most linear production multimeter ever, as my DCV linearity reference, and Keithley 182 nanovolt meter to read the thermocouple output. One of the many disadvantages of thermal voltage converters is that they need a significant current, a couple of milliampere at least, to create the heat that is their central working principle. A current flow through a cable resistance means that there's going to be a voltage drop between the source and the destination, so I've configured the calibrator for 4-wire remote sensing. I'll use the freshly A-CALed 3458A to fine-tune the calibrator's output to as close as possible to 10 volt DC. Another TVC disadvantage is that they have a longish settling time, but after a while the thermocouple reading on the nanovolt meter stabilizes. Then we can zero it digitally, so that we get a zero reading again whenever we inject an equivalent 10 volt RMS signal into the converter. And what do you know, let's do just that. 1 kHz 10 volt RMS coming right up. On the nanovolt meter we can see a short drop in the converter temperature while the calibrator is rearranging itself internally. Let's see what 3458A's electronic RMS sensor has to say about this. Fluke 5700 should be pretty good at this, because if you remember, it uses thermal RMS sensing techniques internally too. But yeah, after 10 minutes of settling time there does appear to be a 108 ppm difference between Fluke's AC and DC ranges, and an even more severe discrepancy in 3458A. Although that is easily within spec because I'm in the power on default analog computer measurement technique. That meter can do much better, I just forgot to switch to synchronous mode, sorry. All of this, of course, only works out if we trust the thermal converters. That's always the catch with second-hand equipment, at least in their most recent calibration in 1993. The 12 volt combo I'm using right now only accounted for a 14 ppm difference. A positive number indicating that more AC than DC was necessary to cause the same thermocouple output. At any rate, we came here primarily to check on Datron Wavetek 4950, and we still have, to the best of my knowledge, a perfect 10 volt RMS signal. Let's see what our multifunction transfer standard has to say about that. What? Is that exactly plus 14 ppm? That has to be a lucky coincidence. Yeah, okay, this is amazingly close, because we are directly on the spot calibration point of interest. Let's try the same procedure at 2 volt. I'll build the most sensitive converter combination for 3 volt. I'll create a 2 volt DC signal based on 3458A, taking advantage of its unmatched DCV linearity. I'll zero out the nanovoltmeter when the thermal converter has stabilized. I'll feed 2 volt 1 kHz into the thermal converter and fine-tune it until the nanovoltmeter reads exactly 0 again. And now, finally in the same 10 ACV range. How does 4950 like it? Yep, that's about what we saw in the automated test earlier. So it wasn't a unique quirk or a problem with the setup. But looking at it now, it's not super bad. The 4950 user manual doesn't specify ACV linearity at all. The closest thing we could go off of is 30-day transfer stability, which is 10 ppm of range. This is out 43 ppm of range, so not sure if it needs an adjustment. Not even sure if I could perform this adjustment if I had to. In the calibration menu there's this password-protected special entry for initial factory-only adjustments. I found that password in the firmware image, and I don't think there is any harm in publishing it now that this product has been discontinued for decades. It's 404824, the phone number of Datron HQ in Norwich. Nowadays Fluke Calibration lives there. Hard to imagine what invaluable treasures must have gone through these dumpsters throughout the years. Anyway, there is this AC linearity option. If I press it, it appears to do something. But I feel like I should be connecting something to the inputs, like 2 different AC signals. I'm not fluent enough in assembly to figure out what is expected here. And I'm not brave enough to press save now and risk my somewhat working baseline calibration. I'll have to keep an eye out for a leaked service manual, or I could try the 4920 procedure, which should be similar. Another thing, since we are all gathered here, last time I was under the impression that this meter could only read its points of interest and would refuse everything else. That is its default behavior, but as Tin from XDevs has pointed out in the comments, you can disable it and easily make it act like a normal multimeter. So while DCV linearity is still not its primary purpose, it should have some of it, and so naturally we have to test it. Here I've configured the calibrator to do a -11 to +11 volt sweep in 250 millivolt steps, which are then observed by both 3458As and Datron. This was a bit of a shocker, I must admit. It is amazingly good, much better than what I would expect from a 7.5-digit class device. I wonder if Datron 1271, which uses a similar looking ADC, is as good as this. I'm publishing the data on GitHub, link below. Similar story in the noise department. It is basically noise-free down to the least significant digit on the 10 volt range. It helps itself to 64 ADC conversions, which are averaged internally, before one high accuracy reading is pronounced every 20 seconds or so. Still, this is amazing low noise performance that a lesser manufacturer would shamelessly release to the market as 8.5 digit, even if the least significant digit would then be noisy and of limited use. I am impressed. Datron Wavetek 4950 uses hermetic bulk metal foil resistors for almost everything, guaranteeing stability for its primary purpose as a multifunction transfer standard. But it's also cleverly built with lots of hidden undocumented qualities, such as fantastic DCV linearity and low noise. It also has a low temperature coefficient in all ranges I've used, combined with a much longer time constant than the 8.5 digit competition, because it doesn't have a stupid cooling fan. I like it a lot, and I'm glad that we could save it from the dumpster. Not a hugely surprising conclusion, but thanks for sticking around all the same. What's next? Nanovolts? Attoampere? Femtoseconds? Or gigahertz?